Today's topic is Stokes Theorem, but let's just quickly review Green's theorem. Okay, what was Green's theorem before we talk about Stokes Theorem? Green's theorem, instead of writing it the weird way that your textbook did, I wrote it like this. F dot dr, vector on some enclosed curve C, was same as the double integral and the region D, and then this thingy cross product called the curl of F, and then we dot that with dA vector. And what did I mean by that, right? So if we have some kind of enclosed curve, and this is C, and then interior is D. And then by convention is counterclockwise rotation. Okay. And then dA is just the upward K direction vector in this case. Do you remember forgetting this before spring break? And then this is the vector was F was given by P, which is function of X and Y, I vector plus Q, and function of X and Y, and then J vector. Good. So I might as well review what the cross product of this side looks like. So if we take a cross product of F, it looked like this. I, J, K, and then we have partial derivative with respect to X, with respect to Y, with respect to Z. Although your book never talks about the Z component, but I thought this was more convenient to have it like this. And then this is 0. So partial with respect to, so I component 0, 0, so you have 0. And J component you have 0, and that's 0, because this is function of X and Y, and you're trying to take a derivative with respect to Z, so that's 0. So K is the only thing that survives. So partial Q over dx minus this one. So partial of P with respect to Y times K vector. That is thingy that goes in here. Do you remember forgetting this? Right, so far with me? And F dot dr is just our usual line integral, F dot dr. And here's the reason that I did it this way instead of doing it the book way, because I was setting you up for Stokes Theorem. Once you're used to that, Stokes Theorem is really nothing else but three-dimensional extension of this. So this is Stokes Theorem. Okay, Stokes Theorem states exactly the same thing. Here's curve C, F dot dr is equal to double integral of some kind of surface now instead of region D. And I'm going to tell you what that means, but still curl of that force dot. Now instead of dA, this is ds. So what does that mean? Okay, I'm going to sketch some kind of surface here. Say that's my surface, and this is the boundary. Okay, so this is the surface S. And the boundary here is still given by the C, and the direction is still counterclockwise. Really? So it could be umbrella or even some Pac-Man monster shape. It doesn't matter. Why would that be true? Is the first thing. Because I kind of proved it here because it was flat, so it was easy to prove. But Stokes' theorem is not that easy to prove because this is not flat. Right? If you flatten this, then do you agree that it becomes exactly this? Even if it's 3 degree, and even if this is 3-dimensional, but not flat on XY plane, if it's hanging somewhere sideways in space, it's the same looking thing, so you know this has to be true if the surface itself is flat. But when it's not flat, why would this be true? And I've seen the original proof of, well, maybe not the original, the PDF version of proof of Stokes Theorem. This is pages and pages long. I've asked multiple professors about it, and most of them either don't want to talk about it or they don't know. But there's a very good insight, and many professors say it exactly like this, and this is how they do it in Caltech. Because I have one of my former students who went to Caltech, and then he came back and told me, this is how they convince you that this is true. Okay, Stokes, let's go back to Green's theorem. Green's theorem is all about this boundary versus interior, right? And what does the coral measure? Coral itself measures the swirly thingies, the rotation on each cell, right? This is what coral measures. Many of these things that are in here. Right, let's say there's some kind of swirly thing going on, like your tornado interior. Good. And then if it's all counterclockwise direction, then our curl overall, if you add it up with the integral, must be positive. That's the whole idea, right? Why would that give us just a boundary? Okay, let's just zoom in. I mean, literally zoom in and look at it. See, there's that direction and there's this direction. So this at the edge, they will cancel each other, wouldn't they? So all of the interior, these curls, the movements cancel eventually. And the only thing that is left is the boundary now, isn't it? That's why this thing on the left-hand side is just a line integral along the boundary. You know what I'm saying? You have to understand and get over this part. Do you get this part? Okay. Well then, let's come back to Stokes theorem. This Stokes theorem is still measuring this swirly thingies on the surface, and we are adding them up. Right? Or better yet, I mean, I'm going to really do it the way the Caltech does. Let's say we put honeycomb shape hexagon in here. And if it's small enough, then it is flat. So Green's theorem applies. You know what I'm saying? Okay, I'm going to put this thing against another shape. Okay, now we are looking at two of them. Do you see in one of them it moves that way and the other one it moves this way because it's positive oriented curve? So that boundary cancels and what we get is just the outside thingy. It's exactly the same thing as what I said earlier, swirly thingy idea. Put three of them together. Then here this thing moves on this direction and this curve, it moves in that direction. So boundaries eventually cancel. So only thing we get left over is the outside thingy. And we can continue to build this thing and expand it everywhere. And eventually all of the interior will cancel if we just fill it up over the entire surface. And only thing that's left is this boundary. You know what I'm saying? And everything else will cancel. So do you agree that without proof, this is like proof by picture, proof by analogy, which is not a proof, that everything this curl that measures inside of this vector function will cancel. And then only thing that you will have left is the boundary, the curve C. And amazingly, this is true. Okay, it's not really setting in, right? So I'd like to take this example and show you how this thing works. It's exactly the same as Green's theorem. Okay. So let's read this example together. So f dot dr, and then f is this. Now we have I, j, k. So x, y, z component, all three of them. So this is what we mean by p, and this is q, and this is r now. So our f, vector f, which is function of x, y, and z, is x, y, p of x, y, z, I vector, plus q of x, y, z, not enough space, j vector. Why do I never give myself enough space? And plus r, x, y, z, potentially all three variable functions, k vector, is what my f is. Okay, this is p, q, r in our case. Okay, and then they say c is this curve right here, and our s is that thingy right there. Okay, which is the intersection of this plane and the cylinder right there. Okay, and we have to evaluate this using Stokes theorem, but I'm going to evaluate it both ways. Okay, so you can see and compare the answers to show you, at least by example, proof by example now, that these two are the same thing. Okay, you usually have to just pick one, and you will always pick the easier one, but here I go with both. So let's figure out the vector function describing C first. Okay, now we have a circular motion in x and y, so let's say cosine t I vector plus sine t j vector. And what do you want to put for z, k component? That much is easy. Somebody who are still doing these things, tell me what the z component should be in order to have this elevation. Otherwise, this thing is flat on this xy plane. Didn't I tell you pretty soon it'll look like Greek if you don't keep up with it? Yeah, now is about time. Doesn't it look like Greek to you? See here, z is equal to 2 minus y, that's the key. So 2 minus y, of course, this is your y. You get it? That's our vector function. You with me? Then we're going to need dr. dr, of course, is a derivative of this. So we have negative sine t I vector plus cosine t j vector, and then minus cosine t. That's not z, that's 2. That looks like 2. K vector times dt. So far with me? Now, before I take a dot product, I think I want to convert f in terms of these things, which is x, y, and z. Okay? Okay, let's look at f. My f is negative y squared, so negative y is sine t, so sine squared t I vector. Are we getting this? Plus x, and x is cosine t multiplied by cosine t, right? So we have cosine t j, and then plus, and then z squared. This is z, so I need to square that. You suck it up and square it. So we have 4 minus 4 sine t plus sine squared t. You with me? Say yes. Let's start then. So we need f dot dr now. f dot dr dotting these two, we have sine qt. And dotting these two, so we have cosine square t. Okay, dotted here, so we distribute with negative, so negative 4 cosine t plus 4 sine t cosine t, and minus sine square t cosine t. The whole thing times the t. You with me? Do any of them combine? I can't believe we don't have any like terms. This is horrible. Okay. In that case, instead of copying that thing, I was hoping that this thing will, some of them will cancel. I just put the integral sign here and put, oh, I already have dr. I'm gonna move this thing a little bit. Not the parenthesis with it. You know what I'm saying? And from now, t varying from 0 to 2 pi. So far, so good. This is the only thing that's going to survive. Do you know that? Because this is sine and cosine, right? This will be used up and eventually they will die because 0 and 2 pi trick. This 0 and 2 pi is the same thing. 0 and 2 pi. You know what I'm saying? So everything will die except this middle term. Correct? You kind of know what I'm talking about, or you want me to actually integrate it for you? Give me an indicator. Do you want me to integrate it, or do you want me to just tell you what happens at the end? Just skipping to the end. So all of this dies. Because of coterminal function 0 to 2 pi. So this is the only thing that's going to survive. Okay, I'm going to integrate that one. So what we will have is 0 to 2 pi of 1/2 plus 1/2 sine 2t dt. And even this thing dies. So all we have is just pi over 2 times this. How about that? Okay. Now, doing it the other way, using cross product, the right-hand side of the Stokes theorem. Okay. Let's calculate the curl. And that is I, j, k, partial with x, partial with y, and partial with z. And our f, which was negative y square, x, and z square. So we have negative y square, x, and z square. Let's take a look at what this thing is. So with I vector, this way is 0, and that's 0. So we have 0, I vector, j vector, negative. This thing is 0, and that thing is 0. So 0 j vector, k vector, we have 1. And this way, plus 2i. Curl tends to make things very, very simple. Okay. Now, then we have to describe the surface, which I'm going to do right here. So this is the headache about surface integral. I'm going to use two variable functions. So R, capital R theta. Yeah, I'll use capital R. And then we'll go to polar coordinate. How's that? Okay. So think of it as just a disk in XY plane for now. So we have R cosine theta I vector plus R sine theta j vector. So far so good, just in XY plane. Now we give an elevation. Elevation, so Z component is still 2 minus this thing, 2 minus y, isn't it? And our y is this now. So not to forget, this is x, this is y, and whatever I'm going to write is z here. So 2 minus our y r sine theta k vector. How's that? Okay, once you have that, then we can calculate ds vector. So let's take a partial derivative with respect to r. And then we have cosine theta I vector plus sine theta j vector plus minus sine theta k vector. And then we'll take a partial derivative with, oh, that's ugly partial derivative with respect to theta now. So we have negative r sine theta I vector plus r cosine theta j vector, and this thingy becomes minus r cosine theta k vector. Okay, so my ds vector happens to be crossing the two imagining I, j, k here. So I term this minus this. So we have negative r sine theta cosine theta. And this way we have negative r plus r. So that's 0. Okay, so we have 0. Okay, now j vector negative 1. This way, negative, let's just do this minus that. So this way, r sine squared theta. And this way, you have, now becomes plus r cosine squared theta. So we just have r. With me? And lastly, k vector. So this minus this. So you have r cosine squared plus r sine squared. So that's r. So far, so good. Now only thing we have to do is dot the two and integrate. Okay, let's do that here. So the double integral over the surface of curl of f dot with ds. Even if I don't put parentheses here, cross product goes first. They are not the equal. Okay, otherwise it has no meaning. Once you dot the vectors, they become scalars, so you cannot cross no more. Okay, double integral here, let's dot them. So this only has k vectors, so these two are irrelevant, it's just that one, correct? Okay, so what we have is 1 plus 2, what is y? Our y is up there. Okay, maybe I'm gonna make a substitution here. This is 1 plus 2. Our y is r sine theta. K vector. Okay. Okay, so we have 1 plus 2 r sine theta. So far, so good. Oh, I have to substitute r, so I have r squared, right? I'm dotting this thingy with that thing. Oh, this becomes r as well. The data. You with me? Now my r will vary. Looks like a unit sphere. Well, no, it's not a unit sphere. It is a unit sphere, right? Yeah, it is a unit sphere. So r will vary from 0 to 1, and theta will vary from 0 to 2 pi. Okay, let's evaluate this. So 0 to 2 pi and r squared over 2 plus 2r cubed over 3 sine theta from 0 to 1 d theta. With me? Pushing these examples down. So that's 0 to 2 pi of this thing becomes 1/2 plus 2/3 sine theta. Okay, once again, our usual trick. Just do it. 1/2 theta plus minus 2/3 cosine theta. Okay? And here's the usual trick. 2 pi, 0. This is the same thing. This thing dies. So this sine and cosine, whenever you're evaluating from 0 to 2 pi, they always die. So the only thing that makes sense is just 2 pi times 1/2, which is pi, which is exactly the same thing we had before. You get it? So proof by example, well, convincing example that Stokes theorem is true. It works. Okay. Next example, we are not going to do it both ways. We'll just take the easier way. Okay? Easier way is, which way would be easier? Let's just think about it. Cool, that's cross product f. People write it like that. Should we create a vector function here, right? And then dot it with f, this f, right? Or should we just go this way? Why don't we just evaluate this and figure it out? Because there are give and take. Using the curl, you have to figure out parameterized surface. That was a headache from here. This part, we have to do this work. This tends to simplify. The other way, of course, you have to figure that thing out. So which is less work is our judgment here. So it all depends on how simple this is, right? So why don't we do this much and think about what we're gonna do? If this is extremely simple, then we'll continue this way. If this looks ugly, then maybe we'll go the line integral way, because that line integral is still flat, so maybe it's not too bad. Let's find out. So we have I, j, k, and then partial with x, partial with y, and partial with z, and your f is xz, yz, xy. Let's cross our fingers, okay? So I component, this thingy with respect to y is just x, and this thingy with respect to just z is x minus y, right? Okay, and comma, and then y component. Let's just do this way. This one, so we have x minus this way with y. Okay, and k component this way with 0, and this way is 0. So at least this is 0. It's not that pretty now, is it? You know what I'm saying? Because now we have to figure out the parameterized surface of this, and that looks like a lot of work, spherical coordinate. So forget it. We're not going to do it this way. We'll just go line integral way. Okay? So line integral way, your C vector function is intersection of this. What is the intersection of this thingy, right? This is a unit circle here, so the radius is 1. Good. So we can say cosine t I vector plus sine t j vector, and plus, how high is this thing? We still have to figure out where this thing intersects, right? Let me draw a triangle like that. Okay, this side is 2, this side is 1. Do you see that is root 3? Okay, it's not that terrible. So dr would be, this becomes negative sine t I vector plus cosine t j vector, and this is 0. Okay, let's figure out what f is. F up here, where is my xy? So xy, let me write it one more time. This is x, y, and this is z. So f is xy here. So we have root 3 cosine t I vector, and yz. So we have plus root 3 sine t j vector, and whoa, I screwed up. X, your f is x, oh no, I didn't screw up. Okay, yz, yeah, I'm good. And then xy is these two. So sine theta, cosine theta, right? So far with me? Now let's start them. So we have f dot dr. And hopefully this will simplify. So here we have negative root 3 cosine theta, sine theta, and sine t. And here we have plus root 3 cosine theta, cosine t, sine t. Wait, these two cancel. Great. And that thingy, is 0. Which is just 0. So what does that tell you about this integral on the surface ds? This will be same as on the curve C, f dot dr. And f dot dr is 0, so this whole thing is 0. How about that? You get it? So this problem originally said, figure out the surface integral by converting it into the line integral. Anyway, they kind of gave you a direction, but if you have to figure out one or the other and you get to have a choice, and this is how you want to do it. You want to evaluate this curve first, then see how ugly or easy that will be. Sometimes this is extremely simplified. Then you want to continue that way. Otherwise, you want to go towards line integral, and hopefully this will simplify.